Hi everyone. So momentum is a concept we need to explain collisions and explosions. That's where we need it. So we come up with the definition of momentum as mass times velocity, as you can see. And the reason is that it's very clear if you think about collision between two cars versus collision between a car and a truck, right? So the result is going to be different if two regular cars collide versus one car collides with a truck. That's easy to see that the mass is an important parameter in collisions. And also the velocity of the two cars is important. Are they fast? Are they going in the same direction or opposite direction? That also changes the result of the collision, right? So it's easy to see that the velocity has to be a component we need to think in collision problems. So we come up with this parameter that we show with most of the time with a lowercase p. Sometimes I saw some capital P's, but general physics we use capital P for power. So the momentum is basically is equal to mass times velocity. So it's a vector because velocity is a vector. So the direction of the two cars that are colliding is important if you think if they're going in the same direction or if they're going in the opposite direction, right? The result is going to be completely different. So therefore, momentum is a vector just like velocity. So when you deal with the momentum problems, you need to pay attention to the direction, which in this case, because its mass is not a vector, velocity is a vector, so the momentum of any object is going to be in the direction of the velocity of that object, in the same direction as the velocity. So the unit is kilogram meter over second because it's basically mass times velocity. So if you take, let's say, any object, it could be car, it could be ball, any object going in toward right in any velocity, let's say v. Let's say this is an object 1 with mass m1 and this is an object velocity at a given moment. So the momentum of this is going to be m1 times v1. Okay, so let's say the mass is, I don't know, 10 kilogram and velocity is given, let's say, 5 meter per second. And the momentum of this object is going to be then 10 kilogram times 5 meter per second. So right now we have 50 kilogram meter or second momentum associated with this object toward right. So again, the direction is important in momentum problems because our object is moving toward right. I didn't use positive sign, but if you remember the direction assignment in one dimension, it was toward right positive and toward left negative, right? So we can follow this direction assignment. So let's say you have another object that goes toward left. In this case, let's say its mass is 5 kilogram and its velocity is 2 meter per second. Let's find the momentum of the second object because it's going left, right? And left is negative and right is positive. So you're going to write m2 v2 for this object and write 5 kilogram times 2 meter per second. But here I want to show you how you show that direction is getting into play in your equations. So because it moves toward left, you need to put a minus sign here in the calculation. So you have minus 10 kilogram meter per second. So 50 kilogram meter per second toward right means because it's positive. For the first object, toward left gives you negative momentum for the second object. So there are different collisions that we can think of. The classifications are mostly elastic collision. If it's elastic, it basically conserves energy too. So elastic collisions is where you have a collision in which energy is conserved. So I'm going to write energy is conserved. And if it's an inelastic collusion, energy is not conserved. So this is the difference between elastic collusions and inelastic collusions. In both cases, though, in both of these cases, in any kind of collusion, momentum is conserved only if there is no external force on your system. So this is the difference between elastic and inelastic collusion. However, let me write this there. If there is no external force, if F net from external force is 0 in your case, momentum is conserved in both cases. And in our problems, that's going to be the case because when an external force does work on your system or effect on your system, momentum is not going to be conserved, and it's going to be a really complicated problem. So we are not going to be dealing with those at this level of physics. So you need to basically remember that in any case of a collusion problem in this course, momentum is going to be conserved. And what do you mean by momentum conservation? If you remember energy conservation, it's basically the total energy was staying the same. So in physics, when you say something is conserved, it means that it's going to stay the same, in a sense that the total amount of that is conserved, right? Energy conservation states that the total energy stays the same, not that energy doesn't change form. It can change from potential energy to kinetic and vice versa. However, the total energy was staying the same. The same thing happens for momentum conservation. So total momentum stays the same, or remains the same, or doesn't change. You can say doesn't change in that case, meaning that for a collusion problem, for example, total initial momentum, whatever that is, before the collusion is going to be the same number as you will find for total final momentum, which is after the collusion. So this is going to be total before collusion, and this is going to be total after collusion. So that's what I'm going to do. So let's take these two objects. Let's say they're just toy cars, remote cars or something. Let's say this one was the number 1 and this one was the number 2. So let's say these are the initial values before these two cars collide. If that's the case, P total initial before they collide is going to be P1 plus P2, the total of everything you have. In this case, we are going to have M1 moving towards right with that velocity I gave, and M2 moving toward left with the V2 I just assigned. Let's say they are basically going to collide on a line, so that this is a one-dimensional problem. So therefore, we will basically add P1 plus P2. And once again, momentum is a vector quantity, so you need to pay attention to the directions when you do this summation. So P1 was 50, as we found, and P2 is minus 10. So when you add these two, you get 40 kilogram meter per second as the initial total momentum. Okay, so let's say they collided head-on like this while they were moving on a straight line toward each other. And in this case of a problem, it might be just, the case might be, generally speaking, two ways. One case that could happen after the collusion is that these two masses go in their separate ways, either toward right or toward left, or one toward left, one toward right, or they might stick together, which is the case where we actually call completely inelastic collision. If the two masses collide and after collision they move together, they merge together and move together, meaning that after the collision their velocity is going to be the same, that is called completely inelastic collision, as it's explained in the book. Let's say in this case it's inelastic collision where they move actually after the collision. M1 moves toward left and M2 moves toward right after the collision, with the velocity v1, let's say final here, or we can put actually v1 final next to 1, v2 final here. So I'm just trying to separate their values from the initial values by putting f for final. In this kind of a situation, you're going to be given one of the final velocity and going to be asked for the other's velocity. Let's say the first car's velocity was given to you. If v1 final after the collision, the first toy car is moving toward left with let's say 5 meters per second, find v2f. Okay, so in this case, what you do is that use this total initial momentum, because as we said, in our case, momentum is going to be conserved in all kinds of collisions. So it doesn't matter what kind of collision it is, but you know that the momentum is going to be conserved because there is no external force applied onto the system. So what you will do is that total momentum is going to stay the same. Okay, so therefore initial total momentum, whatever that was, is going to be equal to final total momentum, which is after the collision. So the initial was 40, as we have found right here, is going to be equal to total final. And what is total final? Basically P1 final, so it's going to be M1 V1 final. And what is it? M1 was, as you remember, 5. So M1 is 5, and V1 final was given to me as toward left with 5. So toward left is going to put a minus sign, if you remember. So my P1 final is minus 25 kilogram meter per second. Therefore, I'm going to write this is basically P1 final plus P2 final, right? So I'm going to write P1 final, which is minus 25, plus P2 final, I'm going to write M2 times V2 final, okay? So, and then I will solve for V2 final. So I'm going to add 25 to both sides to get rid of that minus 25, and this is going to cancel this. So I have 65 on the left, and M2 is, as we had assigned that before, where is it? 5 kilogram. M2 is 5. So 5 times V2F. So I'm going to divide both sides with 5 to get rid of that 5. So I get V2F to be, I change it to the superscript. I'm going to change it to subscript, sorry, because I don't want to use different notations. Superscript, subscript kind of changes. I'm sorry. So V2 final is going to be 13 meters per second, and it's positive. Tells me that it's toward right. Okay, so the direction comes from its sign, and in this case we have basically positive value, so it tells me that V2 final has to be toward right 13 meters per second. So I'm going to make another video for another example. I hope this will help you to understand momentum and collisions a little bit. Have a good day.